Yeah, so this talk is about one of the most fundamental update mechanisms in game theory, and this leads to a specific class of games called weakly acyclic games, and it's considered to be quite important in algorithmic. I mean, this class of weakly acyclic games is considered to be quite important in algorithmic game theory for various reasons. So this talk is essentially about weakly acyclic games, and this is joint work with Christoph Art. So this talk doesn't have anything to do with logic and automata. So I still hope that you find it interesting. Okay, so let me just quickly go through the basic definitions so that I get the notations correct, which will be used later. So a strategic form game, you have a finite set of players, 1 to n, and a game is represented as a tuple like this. So you have the set of players. For each player I, you have a set of strategies, and for this talk we'll assume that this set is finite. And for each player I, you have a payoff function. Okay. So the payoff function is simply, well, it takes as input a strategy profile, a choice made by each player, and it returns a real number. Okay. So this would be an example of a strategic form game. This is a two-player game. There is a row player and a column player. The first entry is the payoff for the row player, and the second entry is the payoff for the column player. Okay. So just some more notations. So strategy profile is simply a choice made by all the players. So it's an element of this cross product, S1 to Sn. And if you fix a player I, then S minus I denotes the n minus 1 tuple where Si is missing in this tuple. And so you get the strategy profile S by adding back Si into S minus I. Okay. Okay, so what is the best response? So best response, a strategy Si for player I is a best response to the joint strategy of the other players, S minus I, if for all Si prime, you have the following condition. Suppose player I switches from Si to Si prime. Okay. The payoff that player I gets is at most what he was getting earlier. Okay. Then you say that Si is a best response. Now, Nash equilibrium, it's one of the most fundamental solution concepts in game theory. It says that, I mean, it's a strategy profile where all the players, every player is playing its best response. Okay, so these are standard definitions. And an example of a Nash equilibrium for our earlier game is this, Ax, because the row player is getting 3. The only way he can deviate is switch to B. He gets a payoff of 1, which is worse, and the column player also does not gain. So that's a Nash equilibrium. Okay, so these were the standard definitions. So let's come to something more interesting. It's called an improvement path. So an improvement path, okay, so firstly, what is a path? A path is simply a sequence of strategy profiles, S1, S2, and so on, which satisfies the following condition. Okay, so you take any two consecutive strategy profiles, let's say Sk minus 1 and Sk in this path. The only difference between Sk minus 1 and Sk is that exactly one player changes its strategy. Okay, so everything else remains the same. So exactly one player changes. So then it's called a path. Okay, and what is an improvement path? It's essentially a path which is maximal, and it also satisfies the following condition, that if a player I changes when going from Sk minus 1 to Sk, then the payoff for player I also strictly increases.
What do you mean by maximal?
So it's maximal, I'm sorry? It can be infinite.
So it's a way to navigate.
Yeah. So you take the set of all strategy profiles, you can define an edge relation depending on whether a player switches and it's a better improvement. Right? So that defines a graph for you, and you take the maximal paths in these. So that's an improvement path. Okay. Okay, so note that when you make the switch from, I mean, when player I changes from, let's say, Sk minus 1 to Sk, I am not insisting that he plays the best response. Okay. So the only restriction is that the payoff strictly increases. It need not be the best response. Okay. So a game has the finite improvement property if every improvement path is finite. Okay. So it's quite obvious that this is a very nice property to have for a game, Why is that? Because this immediately guarantees that there is a pure Nash equilibrium. And what is a pure Nash equilibrium? Well, you start at any profile, you follow an improvement path. It's guaranteed to terminate. You look at the last profile in this path, and that's a Nash equilibrium. Okay? And there's also a very intuitive way of finding or computing this Nash equilibrium, which is that what do you do? Well, you essentially do local search. Right? So you do local search, and what you terminate in is a Nash equilibrium. Now, this does not mean that it's efficient. So it just means that there's an intuitive way of computing the Nash equilibrium. Okay? Okay, so it's clear that not all games have this property. So it's like a restricted subclass of games. So immediately there are two questions which you can ask. How do you actually show that a game has this property? And secondly, are there natural classes of game which has this property? Okay. So let's look at the first question. How do you actually show that a game has this finite improvement property? So there is a very nice technique to do this, and it's called the potential function. So suppose you're given a strategic form game, something like this. A function phi from the set of strategy profiles into the set of real numbers is said to be a potential function if the following condition is satisfied. Okay. So you take some player I. Suppose player I switches from Si to Si prime, okay, and his payoff strictly increases, right? So the difference is strictly greater than 0. Then it also means that if you apply this function phi on this new profile, then the value of this function also strictly increases. Okay. So the important point here is the payoff is indexed by the player identity, whereas this is a global function. There's nothing to do with player identity here. Okay, and the result which was shown by Mondra and Shapley says that every finite game has a potential function if and only if it has the finite improvement property. Okay, this is probably not very surprising because we said that if a game has the finite improvement property, well, you can do local search and find the equilibrium, right? So how do you show that a game has the local search property? Any problem has a local search property. You have to define a progress measure, right? So, and this function is essentially the progress measure. Okay. So then the second question: are there natural classes of games which has this finite improvement property? So there's a very nice. This is a very abstract class of games, which is very useful because it can be applied in various settings, and these are called congestion games. Okay. So what is a congestion game? Well, again, you have a set of players n, a finite set of players 1 to n. There is a finite set of facilities or resources called the set R. Okay. You can think of these, for instance, if you take the road network, you can think of these resources as road segments in this entire network. Okay. Or if you take the computer network, you can think of these as links in a computer network. Okay, so these are just some abstract set of facilities or resources. Okay, so what is the strategy space for each player? For a player I, the set of strategies is simply a subset of the set of resources. Okay, so for instance, again, if you take the road network and if you want to go from a source to a destination, then the set of strategies will be the set of all paths connecting S and T. Okay, in this network. Okay. So now the interesting part is this. So each facility j has a delay or a cost function associated with it. So it's a function dj which takes as argument some number between 1 and n. So 1 and n is the number of players. Okay, so it takes as argument some number between 1 and n and returns a real number. Okay, so what's the idea? The idea is, suppose you have dj of k. So j is a facility or a resource. K is some number between 1 and n. The idea is that dj of k is the delay for using this facility or this resource j when there are k users using j. Okay. So if there are k number of users using this, let's say a road segment, then what is the delay that you experience? That's dj of k. Okay. So given a strategy profile S, which gives a strategy for each player, xj of S, j is a resource again, it's the cardinality of this set. What is this set? It's the number of players I which uses the resource j in its strategy, Si. Okay. Now what is the cost function? So the total cost for each player is simply, well, you sum over all the resource j used by player I, and you look at the cost of that resource. Okay, so our the payoffs are essentially negative costs, right? So the players are trying to minimize its cost, or in other words, maximizing its payoff. So the payoff will be minus of this cost. Okay. Now the interesting, this is a very abstract definition, so you can apply it on road networks, on computer networks, and various other things. Okay. So the interesting result is the following: that every congestion game is a potential game. Okay. So this is interesting, but what is more interesting is that you can actually show the other way around, that every potential game is also a congestion game. Okay, so which gives you a very nice structural result, which says that potential games are essentially congestion games in some disguise. Okay, so it's a characterization result. Okay, so this is so these are potential games. So let's look at something else. What are called weakly acyclic games? Okay, so weakly acyclic games. So a game is weakly acyclic if the following condition holds. You start with any strategy profile S. There is a finite improvement path that starts at this strategy profile S. So remember, potential games said you can start with any profile S. Every improvement path is finite, and it terminates in a Nash equilibrium. Okay, weakly acyclic is slightly different. It's like a for all there exists kind of condition. Okay, so you can start with any profile. There is a path which terminates in a Nash equilibrium. Okay, so this is an example. So this part essentially is a matching pennies game. Okay, so if you start in this profile and you follow the best response improvement path, then you essentially cycle in this path. Okay, but there is a way of escaping this cycle, which is that when, let's say, you start with this profile and player 2 can improve from -2 to +1. Okay, so it's not a best response, but player 2 can still improve to +1. And once he improves here, then player 1 can move to 3-3, which is a unique Nash equilibrium in this game. Okay, so this game is weakly acyclic because it doesn't matter which profile you start with, you can always end up in this unique Nash equilibrium 3-3. Okay. This was defined by, this was introduced by Peyton, yeah. Oh, it's a one name, is it? Okay. Right, so what is the idea behind weakly acyclic games? The idea is there could be, potential game says if you look at this graph, this improvement graph, then there are no cycles. Okay. Weakly acyclic game says there could be cycles, but the point is there is a way of escaping the cycle at every point. Okay. There is a particular path that you can choose such that you can always escape the cycle and terminate in a Nash equilibrium. So that's the difference. Okay, so are there natural classes of games which fall under the weakly acyclic category? Of course, every potential game is a weakly acyclic game, but are there other classes of games? So we saw what is a congestion game, right? So the important point, okay, let me just go here. The important point in a congestion game was this delay function just depends on the number of players using that particular resource. It does not depend on the identity of the player. Okay. Now, if you have a congestion game where the delay function or the payoffs essentially depends on the identity of the player, not just the number of players. So for instance, in a road network you can say, well, if there are more trucks, then there'll be more congestion, right? So it actually depends on the identity of the player. Then these games are not potential games. They need not have the finite improvement property, but it can be shown that these are weakly acyclic games. Okay. So there are natural classes of games which fall under this category. There are plenty of such games. So, okay, so one important point in both potential games and weakly acyclic games is the property that you let exactly one player update at a time. Okay, so suppose you take the standard game of Battle of Sexes. So this game has two equilibria. This is one equilibrium and this is one equilibrium. Yeah. Now, if you take a profile something like this, then both players, row player and column player, they are both not happy with this profile, right? So, if you let one of the players update, let's say you let the row player update, then he updates here, it's a Nash equilibrium. If you let the column player update, then he updates here, again it's a Nash equilibrium. Okay? But the point is, if you let both players update together, then you reach this profile, which is again not a Nash equilibrium, and they just keep oscillating between these two profiles. Okay? So in both potential games and the weakly acyclic game, it's very important that you let exactly one player update, and you do not let, you don't have concurrent updates. Okay? So, here it doesn't really matter, right? The only improvement is the best response update. But in general, you don't have to assume that. Okay, so yeah, so that's an important property that in both potential games and weakly acyclic games, you have this restriction that exactly one player updates, and you cannot have concurrent updates. Yeah.
There is a point to this question. In general, the improvement, whether improvement is to the best response or to some response,
Yeah.
matters.
Yeah. So yeah, in general it does matter. In potential games it does not. So that's what. Weakly acyclic games it does. So even that early example, if you do a best response update, then you just keep cycling, and the only way of exiting that cycle is to do a better response, not a best response.
So you don't know.
You don't know. Yeah. Right. Okay. So the point here, the point that I'm trying to make is that potential games and weakly acyclic games, there's a kind of a global authority, a central system, which has to come and tell you which player can move at any point of time. Okay, so if you don't have that, you might keep oscillating. So this existence of this global player is kind of hidden in the definition. Okay, so let's try to formalize this, because it turns out to be important in many cases, explicitly having this global player present. Okay, so let's try to formalize this, and we do it in terms of a scheduler. Okay. So you can think of a scheduler as simply a function f. It takes as input finite prefixes of strategy profiles, and it produces on its output a player identity. Okay. So what's the idea here? The idea is the following. So a scheduler, suppose you give it a sequence S1 to Sk, okay, of joint strategies, such that the last strategy here, this last profile here, is not a Nash equilibrium. Okay. Then it will pick a player in this last profile who is not playing a best response. So that's the idea. Okay. So we say that an improvement path S1, S2, and so on respects a scheduler F. If you take any two consecutive strategy profiles, let's say Sk and Sk plus 1, the only difference is, let's say, player I changes. Okay. Then this player I is actually scheduled by the function F. So it's a restriction on the set of improvement paths. You have to make sure that the player who changes is actually scheduled by the function f. Okay. Okay. So in this language, what is a potential game? Well, we can rephrase it as follows. You take any scheduler f. So it says the following. So for all schedulers f, for every improvement path in G which conforms to f, which respects f, this improvement path is finite. So that's what essentially potential games mean. Right? Doesn't matter which scheduler you pick, doesn't matter which improvement path you choose, it's always finite. Okay? But this fact that there is a scheduler is very important. Okay? So weakly acyclic games, so this is like a for all quantification. Weakly acyclic is again for all their excess quantification, right? So there is a scheduler f, and there is an improvement path in which that path is finite. Okay? It doesn't matter which profile you start with. There's always a scheduler you can pick, and there's always an improvement path which is finite. Okay? So what we are essentially interested is something. So what is the underlying question? The underlying question is how much of global control do you need for the players to make sure that the players actually find a Nash equilibrium. Okay? So for potential games, it says, well, you don't really need too much of global control. You can let players selfishly update. As long as there is a reasonable scheduler, it will find a Nash equilibrium. Weakly acyclic game says you need a lot of global control because you need a scheduler and you also have to tell the players how to play. Okay? Only then it will reach a Nash equilibrium. Okay? So the underlying question is how much of power the central authority needs to drive the players to a Nash equilibrium. Okay? So the essential question that we want to ask is, is there a scheduler F, I mean given a game, is there a scheduler F such that all improvement paths in this game which respects this scheduler F is finite. Okay. Okay. So sorry. So if the question that we are trying to ask is how much of power does the central authority need, then the first thing that you'll notice is well, how much of power does this scheduler need, right? So it's right now it's defined over finite prefixes. I mean, it can see all its entire history and then choose a player. Okay. So there are different ways of defining schedulers in restricted manners. So we can say, well, the scheduler does not really depend on the entire history, but only the last state. Okay. This will be like a memoryless scheduler. Okay. You can impose further restrictions. You can say it doesn't even depend on the last state. The only thing it depends on is the set of players who are not playing their best response in this last state. Okay, so it can't even see the entire strategy profile. The only thing it can access is the set of players who are not playing their best response in that last state, in the strategy profile. Yeah.
The scheduler you want to do, this one, you can see the entire graph as a one-player game.
Yeah.
It's a kind of control problem also to enforce reachability to on situations where there is no improvement, right?
Yeah, but I mean, you want to make sure that, so a scheduler is defined like, so you pick a player, but then after you pick a player, the player has complete control over how he updates, right? So it's not just finding a path in this graph. Yeah, so finding a path in this graph will be weakly acyclic. So that's what weakly acyclic says. Yeah, so that's the point. So you give full control, I mean, full freedom for the players once you pick the player. Okay. So I mean, the question is how much of it's yeah, essentially if you look at it that way, it's a two-player game. Yeah. Okay, so you can say, yeah, no problem.
And you may specify a problem in, say, ATL logic. If you have those two players, so you want the scheduler to have a strategy so that the opponent isn't forced to eventually reach a non-improvable situation.
Yeah, so I'll just come to that in a minute. I mean, yeah, I mean, so in general, these paths can be long, so you can't, I mean, maybe I didn't get your question.
I'm not missing the point because I don't see why you need memory.
Oh yeah, that I'll come to that in a minute. Yeah. So what I'm saying is, I mean, of course, this is state-based, but you can have further restrictions on the scheduler, right? You can say that the scheduler can't even access the entire state, but it has to make a decision based on just the number of, I mean, on the identity of the players who are not playing best response, for instance. Okay, so this is a restricted class. It's a further restriction. You can even look at further restrictions of the set-based scheduler, what are called local schedulers, which is that you first fix a permutation of the set of players. Okay, you fix some permutation pi of the set of players. Now, the scheduler is always forced to pick the pi first unsatisfied player. Yeah, so this is again a further restriction. Okay, so the idea is, I mean, our idea is to essentially look at what is the minimal kind of global control that you can give, so that the players still find an Nash equilibrium. Okay, for that, so that's the motivation behind defining these restrictions for schedulers. Okay, and as you said, okay, so how does this picture look like? You have potential games sitting here, games with FIP. This sits inside weakly acyclic games, and this containment is strict, which is very easy to show. And class scheduler sits, it contains FIP, and it sits inside weakly acyclic games. Okay. Now, I mean, of course, these various schedulers that I defined, this inclusion is very straightforward. If if a game has the finite improvement property, then obviously it has a local scheduler. If there is a local scheduler, obviously it has a set-based scheduler, and so on. Okay. At the very end, you have this weakly acyclic games. Okay. So this inclusion is very, very direct. are these inclusions proper? Okay, so that's one question. And the first result is what you just said. You don't need to look at history. You can just look at memoryless strategies. Okay, so the proof is essentially the same as what you'd use to show that reachability games are memoryless determined. So instead of the reachability set, you just start with the set of all Nash equilibria, because that's the set that you want to reach, and then just do the fixed point computation. So you can show that the game respects a scheduler. If the game respects a scheduler, then this fixed point that you reach is essentially the set of all strategy profiles. Okay, and the other way around, if this holds, if the fixed point is same as the set of strategy profiles, then you can actually build a state-based scheduler. Okay, so you don't need to look at prefixes, you just need states. Okay, so you can also show that. So if you look at, so in general I said these are improvement paths, right? So now if you restrict your attention to just best response paths, these are not general improvement paths, but the players are forced to perform their best response. Okay, so if you look at best response path, and suppose you have a scheduler which terminates under best response, then you can also build a scheduler which terminates under better response. Okay, so how does this picture look like finally? Well, here you have, I mean, these two classes are the same. You don't need prefix, you don't need history. You can just do it with state. Everything else is a strict inclusion. Okay, and so for each of these classes, you can again look at the best response. I mean, so here it's just improvement paths. Here you're restricting to best responses. Okay, so you're not allowed to do arbitrary improvements, but you're forced to do best response. If you do that, you get the same classes with best response, right? So here what you can show is these four classes are the same because of this result. Everything else is a strict inclusion. Okay. For two-player games, it gets a little better because all the best response classes are the same, and there are some strict inclusions in the improvement path. Okay, so these are kind of the hierarchy which happens. So inside this entire set schedulers, you have this this hierarchy. Okay.
Enforcing the best response amounts to enforcing some better response with a finite time.
If you have state-based schedulers, then you can do that. That's what this result says. But if you restrict your schedulers to be, for instance, set-based or local, then you cannot do that. So you cannot simulate a better response scheduler. Yeah, for two players it becomes a lot easier because yeah, I mean I can. It's a bit. I can discuss with you later. Yeah. Okay, so what do we have? So finally, so if you look at potential games or games with finite improvement property, then you have congestion games and various other kinds of games. If you look at weakly acyclic games, you have natural classes of games which fall into the weakly acyclic class. And so the question is, are there natural classes of games? I mean, of course, you can always build some matrix form games, but are there natural classes of games which fall under this class of schedulers? Okay, so for this, we look at what are called cyclic coordination games. So these are essentially coordination games, but you have a graph structure on it. Okay, so how does this work? So first you assume that there is a special strategy T0, which is common for all the players. So this is something like a null strategy. Okay, and so this notation just means you are doing increment and decrement mod n. N is the number of players here. Yeah. Yeah. So in that hierarchy, we have not actually looked at fair schedulers, but I'll come to fair schedulers in a minute, in a different context here. Okay, so it's essentially a coordination game, except that you have a cycle structure here. So the players are kind of in a cycle, and the idea is, so the payoffs are defined as follows. If you play this null strategy, then of course you get a payoff of 0. The idea is essentially each player wants to coordinate with its predecessor. Okay, so if it coordinates with its predecessor, it gets a positive payoff. If it does not coordinate, then it gets a negative payoff. Okay, so it's essentially a coordination game, except that there is this special null strategy. You can choose not to play anything, and you have this cyclic structure. Okay, so here you can show that each coordination game, each cyclic coordination game respects every local scheduler. So it doesn't matter which scheduler you pick. All the improvement paths are finite, and it holds for local schedulers. So you don't even need the access to the state. Okay. So of course you can easily, so the one thing that you can easily show is cyclic coordination games are not potential games. You can show easily that they are weakly acyclic games, but how much of global control do you actually need? Well, this result says that you don't need too much. Okay, you just need local schedulers, so you can let players update selfishly for most of the time, and it doesn't really matter which scheduler you pick. Okay, so you have a lot of freedom here for cyclic coordination games, and this is precisely the kind of results that that makes sense in this setting. Okay, so the contribution or the idea behind looking at these schedulers is twofold in our opinion. One is that it gives a precise characterization of weakly acyclic games. Okay, how much of global control do you actually need to solve these weakly acyclic games? So, for instance, a nice result in this context is, for instance, we saw that if you take congestion games and if you have player-specific payoffs, we already saw that it is not FIP. It does not have the finite improvement property, but it is weakly acyclic. That was already known. And a recent result, this is again using schedulers. They show that for such games, you actually just need a local scheduler. Okay, so under best response, if you follow a local scheduler, then you can solve these games. You can find an equilibrium. And this result is also tight in the sense that if you do not have best response, then no local scheduler will work. Okay, so local is kind of the minimum that you have, right? So under best response, it works. If you do not have best response, then it doesn't work. Okay. There are some these internet routing games which are known to be weakly acyclic games. Again, you can show that you don't really need the entire power of weakly acyclic games. You can define state-based schedulers for this. So this is, this is one nice property of having this characterization. You can precisely characterize weakly acyclic games. The other nice property is on improving complexity bounds. Okay, so in general, potential games has this intuitive way of computing the Nash equilibria. You do local search, except that these paths might be too long. Okay, so in general, it's supposed to be PLS complete, so we don't know a polynomial time algorithm for this. So there are some certain kind of network connection games which were shown to be potential games, and where it is guaranteed that a path, any arbitrary path, will have polynomial length. Okay, and recently it was shown, again using a notion of schedulers, that you can use a particular scheduler to actually show that you can compute the Nash equilibrium, or there is a particular path which you can follow, which is of length n log n. Okay, and this is also optimal in the sense that you cannot compute. It's also a lower bound on computing Nash equilibrium. So this path is actually optimal. Okay. So yeah, giving precise characterization of weakly acyclic games and improving complexity bounds, these are two of the contributions of looking, two advantages of looking at this finer classification of weakly acyclic games. Okay, so that's one part of it. The other is something which we found interesting because, so this update mechanism is very fundamental in game theory. There is another fundamental notion in game theory called the strategic dominance. Okay. And there is a particular relationship between update mechanisms and strategic dominance. So what is strategic dominance? So the first, the most obvious definition is what is called strict dominance. So a strategy SI for player I is said to be strictly dominated if there exists another strategy SI prime of player I such that no matter what the other players play, for all S minus I, if player I switches from SI to SI prime, then he gets a better payoff. Okay, so it doesn't matter what the other players are playing. If player I switches from SI to SI prime, then he gets a better payoff. Then SI is said to be strictly dominated. Okay? So if you take the standard prisoner's dilemma game, then the strategy cooperate is strictly dominated by the strategy defect, for instance, for the row player. And the same thing holds for the column player. That's why you get this unique Nash equilibrium 1-1. Okay? Okay, so this definition is for pure strategies. But you can also define strict dominance with respect to mixed strategies. Right? So you can say that strategy SI is strictly dominated by, instead of SI prime, you have a probability distribution, a mixed strategy. Okay, it's the same definition. Now there is a notion which kind of encapsulates all these, and this is called a never best response. Okay, so what is a never best response? Okay, so it says the following. So a strategy SI is a never best response if for all strategies of the other player, S minus I, there exists an SI prime such that if player I switches from SI to SI prime, then he gets a better payoff. Now what you should notice here is the change of quantification. Yeah, so this says there exists for all, and now you have for all there exists. Okay, so this is precisely why it also captures mixed strategy dominance. Okay, so let's look at an example. So in this example, I claim that C is a never best response. Why is that? For the row player, of course. Why is that? Well, suppose the column player is playing X, then the row player is better off playing A. Yeah? If the column player is playing Y, then the row player is better off by again playing A. But if the column player is playing Z, then the row player is better off by playing B. Okay? So there need not be a uniform strategy which dominates, but there could be various other strategies. Okay? So that's the idea behind never best response. Okay, so if a player is rational, so the idea is if a player is rational, then he would, I mean, you can say that he'll never play a strategy which is never best response, because no matter what the other players play, there's always a better strategy, right, than this strategy. So you can kind of eliminate this strategy from the game. Okay? Okay, so suppose you eliminate this strategy, then you get a sub game where you don't have this strategy, right? So this is like a sub game. Now you can do the same thing, and you can see that this strategy Z is now never best response for the column player. Okay. Again, you can eliminate it. Now you get a sub game, which is this 2x2. Now you can do the same thing. I mean, you can keep iterating this, and what you get is a unique strategy here. And you can show that, so I mean, this process of eliminating strategies is called the iterated elimination of never best response. Okay. Now, a game is set, I mean, you say that a game can be solved by IE and BR if you do this elimination process and you get you get precisely one strategy profile. Okay. So the result is, the theorem is, if a game can be solved by IE and BR, then of course it has a Nash equilibrium, because what you get is a Nash equilibrium. But the important point is it has a unique Nash equilibrium. So you're not throwing out any Nash equilibrium in this process. Okay? And it's also known that you can do this elimination in any order that you wish. It doesn't really matter. Okay? So you can, for instance, instead of going row and column, you can do column row. Or you can even concurrently eliminate strategies. That also doesn't matter. Okay? What you'll always end up with is this unique Nash equilibrium. Okay? So this notion of strategic dominance is very fundamental in game theory. If you, for instance, teach a course in game theory, this is something that you'll do in the first or second lecture. So why is this interesting for us? Well, because of this result here, which says that if a game can be solved by IE and BR, then it respects every fair scheduler under best response. Okay? So, I mean, if a game can be solved by IE and BR, means that there is a unique Nash equilibrium, and you terminate in this Nash equilibrium. Well, then it means that you pick any scheduler, as long as it is fair, every improvement path is finite.
How is fair?
Yeah, so fairness essentially means that if a player is not happy, then you eventually schedule it, or it becomes happy because of the actions of the other players. So there's no starvation in terms of a player not being happy, not playing his best response. Okay? Okay, so I mean, there are some technicalities in this result, but the basic proof idea is very simple. So let me try to explain that. The proof goes as follows. So the first thing you do is define what is called a block. Okay? A block is simply a finite sequence of strategy profiles, S1, S2 up to Sk, such that you take every player I who is not playing his best response in this first strategy profile S0. Right? So you take every player I who is not happy in this first strategy profile. Okay? It says that there is some strategy here where he actually becomes happy in this block. Okay? So it could be that other players change and he becomes happy, or it could also be that he is scheduled and then he becomes happy. Okay? So this is called a block. And so the assumption is, the premise is that the game can be solved by IE and BR. What does that mean? There is a finite sequence of reductions, game reductions that you can do, going from G0, G1. G0 is the initial game. You can remove some strategies, go to G1 and so on, and you reach GM, which has a unique strategy profile. Yeah, so that's the meaning of IE and BR. Okay, so by the order independence result, it doesn't matter how you remove strategies. You can always get to some, you can always get some sequence of removal of strategies such that you solve the game. Okay, okay. So let's assume that F is any fair scheduler, and and rho is a best response improvement path. Okay, which respects this fair scheduler F. What do we have to show? We have to essentially show that this improvement path is finite. Then we are done, right? Okay. So the first observation is that this improvement path can be split into blocks, minimal blocks. Okay. So it's essentially a concatenation of these minimal blocks. That's very easy to see. So you have these. So you have this improvement path which is split into minimal blocks. You take the first block, which looks something like this. Okay. Now you take the first strategy, which is eliminated when you go from G0 to G1. Okay. So this says that the strategy S1 of player 1 is eliminated. That's how you get G1. Okay. Now there are two cases. In this first profile here, suppose player 1 is actually playing S1, which is the strategy which is never best response. Okay. Well, if he's playing S1, then it's never a best response. So whatever the other players do, it will never become a best response, right? So, but we know that this is a block. This B0 is a block. So eventually he's scheduled. When he's scheduled, he of course moves to his best response. Okay. Now once he moves to his best response, he'll never switch back to S1. Why? Because it's never a best response. Yeah, no matter what the other players do. Okay. So that's the first case. If the strategy used by player 1 here is not S1, then again player 1 will never choose S1 because it's never a best response. Okay, so the summary is that the strategy S1 will never appear in this prefix B1, B2 and so on. Why? Because it's never a best response, and this prefix essentially lies in the subgame G1. Yeah, so you're going from G0 to G1 by eliminating this strategy. Now this prefix of this improvement path will lie in this subgame G1. Okay. Now you continue doing this. You're guaranteed that GM has exactly one strategy profile. Therefore, this path has to be finite. Okay. So that's the underlying argument. Okay. So the result essentially is that if a game can be solved by IE and BR, then G respects every fair scheduler under best response, right? So we also had a result earlier saying that if you have a scheduler under best response, then you can also build another scheduler which works under any improvement path. Okay, so that's also fine. The difference between this statement and this statement is that you cannot say for all better response schedulers. Okay, okay, so that's one aspect of it. So the other thing is okay. So this the idea behind scheduler was to look at how much of global control you need. Okay. Now the existence of scheduler itself is a bit artificial, because if you're looking at a distributed system where these players are some kind of nodes in a distributed system, then you cannot even assume that there is a global player who comes and tells you when to move. Okay. Now suppose you don't have such a global player. Okay. What happens? Well, you just look at your payoffs and decide, if I'm not playing my best response, maybe I want to update. Okay. So then what you'll have is a kind of a concurrent update mechanism. Okay. Now the nice thing about these games of IE and BR is that it doesn't matter whether you're doing it sequentially, it doesn't matter whether you're doing concurrently. Okay, these schedulers will always terminate. Okay, so in particular, you can look at a kind of a maximal scheduler, which at every strategy profile S picks all the players who are not playing their best response and schedules them. Okay, so it's no longer sequential; it's a kind of a concurrent update. So we saw that even if you take potential games, if you do concurrent update, it may not terminate. Right? You can get into oscillations. But if a game can be solved by IENBR, then it doesn't really matter. Even if you do a concurrent update, it still terminates in the Nash equilibrium. Okay, so that's one aspect of it. The other thing is, I mean, you don't even need synchronous communication. You can look at situations where these update messages are actually delayed arbitrarily. The only guarantee that you need is that the messages actually, the messages reach the destination. Okay, so this is a very nice class of games in this respect, as far as schedulers are concerned. Okay. Again, so the interesting thing would be to show something like a characterization. So this is again just one direction of it. The interesting thing would be to show some kind of a characterization. Remember that in potential games you had this very nice structural characterization which said that potential games are same as congestion games. Okay. For weakly acyclic games, we don't have any such a characterization. The best that I know of says something like, so if you take a game and you can say that suppose all the subgames have a unique Nash equilibrium, then you can show that such a game is a weakly acyclic game. Okay? That again is not a characterization because it doesn't go the other way around. Okay? So getting a structural characterization for weakly acyclic games, I think, is very important. And our idea, I mean, what we hope is that using schedulers, you get you can make some progress on this front. Okay, so that's one. I mean, that was one motivation of looking at this whole notion of schedulers. On a more positive note, we can actually show that schedulers are very useful to precisely determine how much of global control you need for players to terminate in Nash equilibrium. And it's also useful to improve complexity bounds on finding these improvement paths or finding Nash equilibria in games. Okay, so yeah, let me stop there. And I'll be happy to answer questions.